Hello, everybody, and welcome to the Great Lakes Science Center. My name is Jared, your friendly science Viking, here today to talk about electricity. Specifically, we are going to talk about the Tesla coil. Now, a long time ago, a man named Nikola Tesla invented this machine, and then, fun fact, in science, when you come up with something, you get to name it after yourself. He did just that and named it the Tesla coil. It's just a fun perk of being a scientist. Who knew? Anyway, moving on. So, our Tesla coil works very simply, very interestingly. I could tell you, it'd be way more fun to show you. All right. Now, just to warn you, this is going to be a bit loud. So cover your ears, maybe turn the volume down a bit, whichever keeps your ears safe. And here we go in 3, 2, 1. Racing. All right. So what just happened? You have the means of answering that question, so I'll do it for you. What happened is when we turned the power on, our Tesla coil started to generate a charge. Now, this charge filled my Tesla coil top here with some free-floating electrons. So, quick lesson. Everything in the universe is made up of atoms. You, me, the coil, this table, everything made up of atoms. Inside these atoms are things called subatomic particles. These are our protons, our neutrons, and our electrons. Right now, we're going to care the most about the electrons because they're what we use for the Tesla coil. Specifically, the electrons are the ones that like to grab onto other things. They like to form bonds with other atoms. So right now, when I turned not right now, obviously, when I turned on the Tesla coil, we had a lot of free-floating electrons. A lot of charge had built up. Now, second rule of the universe, everything requires balance. If you have a hot and a cold thing, they'll meet in the middle. Same principle goes with our Tesla coil. So if it had all of these free-floating electrons just hanging out here, they have to go somewhere. They can't just exist. There has to be balance, which is what happened when we introduced this grounding wire. Now, my grounding wire, when I brought it close, has a metal tip. Metal, by the way, is an excellent conductor. That means it allows electricity to flow through it really easily. So write that down, conductor, not the music kind. So they're fun too. Not important, I get distracted. Moving on. So when my grounding wire got close enough to my Tesla coil, my electrons, all my free-floating ones, jumped to my grounding wire and then went out to my base and then into the table, into the ground. The ground, by the way, the Earth, the planet we stand on, has infinite charge. It can balance out anything that comes our way. So when you see a lightning strike, that's actually some free-floating electrons balancing out between the sky, the clouds, and the ground. Now, we always think that the lightning will come from the clouds to the ground, but actually, not always the case. Sometimes to have proper balance, the electrons have to move from the ground to the clouds. Rare, but it happens. Same kind of principle behind our Tesla coil. It requires balance. So if it has too many or too little electrons, my grounding wire will help balance that out. Now, here's the thing. Electrons are incredibly small. We can't see them. So can we see them moving? I'll answer that myself again. No, because they're too small to see. All we can observe are the after effects. So we observe the electron movement as it created heat, as it created light, as it created sound. So that's the electricity as we know it. That's the lightning that we know. We don't actually see it. We only see its after effects. We don't see what it does. All right. We'll do this one more time because it's always fun. Ready? Brace yourselves. 3, 2, 1. That never gets old. All right, folks. That's all the time I have for today. Thank you so much for joining me. Hope you have a good day. Hope you can find more science things to play with. Until next time, everybody, have fun, be safe, and as always, stay curious.